Welcome to today's discussion from Chapter 5's coverage on thermochemistry. It's wonderful to have you here. Before we get into today's topics, I wanted to begin by telling you a story that was shared with me by my PhD advisor back in graduate school. Many years ago, back when he was in graduate school, he told me that there was an undergraduate who was new to their research group, who was nervously awaiting the first time in which their advising professor would actually come down and visit with them in the lab. This undergraduate happened to be particularly nervous and was pacing back and forth and taking his hands in and out of his pockets. Looked all around very scared to actually have the opportunity to meet his advising research professor in the lab for the very first time. When the professor arrived and began his tour of the lab discussing various aspects of the research with the postdocs and graduate students, he happened to pass nearby this undergraduate who had at this time yet had the opportunity to visit one-on-one with him. The undergraduate was undoubtedly feeling a great amount of anxiety and intimidation upon seeing his professor at such close quarters. Needless to say, for some reason that's slightly inexplicable, the graduate student accidentally turned swiftly around and knocked a $5,000 rotavap off of the edge of a bench, which hit the ground and shattered into a million pieces. While the supervising professor might have decided to murder this undergraduate on the spot, his response was a little bit more humorous. He shook his head back and forth, got a cigarette out of his back pocket, lit it, and then just left to never return. I have no idea if that undergraduate ended up continuing a career in science. After today's lecture, you should be able to know the 7 polyatomic elements, define the various terms listed here, know what a state function is, explain the concepts underlying enthalpies of reaction, and make calculations using the thermodynamic equations discussed in sections 5.1 through 5.4. Before beginning, I want to give you a warning and an introduction. The material covered in this lecture, which comes from sections 5.1 through 5.4 of our text, is extremely conceptual, which means that we won't be working as many problems as usual in this lecture. I'll instead be introducing you to various principles and concepts of thermodynamics. I will very shortly begin by reading some introductory paragraphs from pages 159 through 160 of our text. But first, I want to teach to you this principle of polyatomic elements. Now, the following 7 elements are called polyatomic elements: hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. You're welcome to look at where they lie on the periodic table just so that you can memorize which ones they are. These elements cannot exist as single uncharged atoms in their elemental forms. In other words, there's no such thing as uncharged H, O, N, F, Cl, Br, or I. In its elemental form, hydrogen exists as H2. The same thing goes for the rest of these elements. They exist as N2, O2, F2, Cl2, Br2, and I2. These can exist, however, as single charged atoms such as H+, Cl-, Br-, and so forth. Now, this rule applies uniquely to polyatomic elements and not the remaining elements on the periodic table. With that said, I'm now going to teach you the definitions of various terms that are essential when talking about thermodynamics. The first one is energy. Simply defined, energy is the capacity to do work or transfer heat. So that begs the question, what is work? Well, work is the energy used to move something against a force. A work's magnitude equals the product of the force, F, and the distance, d, that the object moves, according to this equation. The definition of energy also begs the question, what is heat? Well, as we define it in the world of thermodynamics, heat is the energy used to increase something's temperature. It's important for you to remember that work is often abbreviated as a lowercase italicized w, and heat is often abbreviated as a lowercase italicized q. You might ask, why in the world didn't they use the letter H? I'll explain that later on. So I want you to tell me whether each of the following energy expenditures represents work or heat. Example 1, someone throwing a baseball. Now keep in mind that work is equal to a force applied to an object multiplied by the distance that travels. I think we can all agree that this is an example of work. How about striking a match? This particular example might represent both. The actual act of striking requires moving an object against a force over a small distance. That is work. The actual energy given off by the burning match, however, is heat. How about using a gas burner to boil water? Once again, depending on which aspect of this process we're discussing, this might represent either work or heat. And how about enduring a terrible first date? Well, I don't know the answer to that, but I'll let you figure that out on your own. We now move on to discussing energy a little further. As it turns out, there are two different kinds of energy. One of them is kinetic energy. Kinetic energy is the energy of motion. If a system is actively producing or exerting energy, we call that energy kinetic energy. An object's kinetic energy, which is often abbreviated with the symbol E sub k, is described using the following formula. E sub k equals 1/2 mv squared, where m is the mass of an object and v is the object's velocity. Now, the international or SI units for energy is a joule, abbreviated as a capital letter J, which actually is a shorthand way of writing kilograms times meter squared per second squared. Now, you're welcome to see page 162 of our text to analyze why that is a little further. Now, 1 calorie, which we often hear about, equals 4.184 joules exactly. And a calorie with a capital letter C that we talk about in nutrition is actually equal to 1,000 lowercase letter c calories. Thus, we remember these values here. I do not require you, my students, to memorize these because I will give them to you on the exam and problem sets. The second type of energy is potential energy, which simply defined is stored energy. If a system is positioned to be able to produce energy, but isn't actively exerting it, then we say that that system has potential energy. That is, it has some additional stored energy in it that has yet to be given off. So let's see if you can figure this out. Are each of these things shown examples of kinetic energy, potential energy, both, or neither? Example 1, a rock at the top of a hill. You note that if the rock is stationary at the top of the hill, it isn't actively producing or exerting any energy at all. However, does it have the potential of being able to do so should we nudge it to the edge and let it start rolling? Absolutely it could. And if any of you guys have had the environmentally unfriendly experience of rock rolling in the mountains, you'll note that large rocks do indeed exert or produce a large amount of energy as they tumble down a hillside. Thus we would say that a rock that is stationary at the top of a hill has high potential energy, but no kinetic energy. How about this? A rock that is in the process of actively rolling down a hill. Well, you'll note that if it's partway down the hill, it is exerting or producing energy as it rolls. Thus, it does have kinetic energy. However, does it still have potential energy? Yes, it does. If it hasn't reached the bottom of the hill yet, where it once again regains a stationary state, it indeed still has some potential energy, the amount of energy that it's going to potentially give off as it continues rolling down the hill. Once it gets to the bottom of the hill and is no longer in a position to give off any energy, it now has zero potential energy. Now, I'm not going to analyze the rest of these examples, but would like you to consider them on your own. A rock at the bottom of a hill. A bowl of cereal. Keeping in mind that we actually eat cereal and extract the nutrients therein to use as energy. An unlit stick of dynamite. A battery. And exploding dynamite. I now want to show you some cool videos, really just because they're funny. In this first video, taken from YouTube, we see someone longboarding from the top of a very large hill. I only have one question for you. When that person is at the top of the hill, does he have high potential energy, high kinetic energy, both, or neither? While actively skating down the hill, what is the answer to that question? And what would the answer to the question be once he is at the bottom of the hill? I now want to show you another video talking about the energy given off when a gas cylinder is punctured. It's also a very interesting video that illustrates the importance of lab safety when dealing with gas cylinders. I want you to ask yourself the question. At each state shown, does the gas cylinder in question have high potential energy, high kinetic energy, both, or neither?
When a typical cylinder is filled to its design pressure of 2400 psi, It will contain almost 300 cubic feet of atmospheric pressure gas, or about 160 times the internal volume of the cylinder. This compression of gas represents a tremendous amount of stored energy. If the outlet valve is broken off, the sudden release of compressed gas can turn the cylinder into a missile with energy to shoot through a cinder block wall. In one reported incident, a damaged cylinder penetrated 2 sheet metal walls before becoming airborne and exiting through the roof. The tank reached an altitude of 140 feet before falling back through the building's roof a second time. When a steel cylinder becomes a projectile, it can move with great force, at high speeds, and in unpredictable directions, with the potential to cause serious or fatal injuries.
So this is the take-home. Once again, thermodynamics is the study of energy and its transformations. Energy is typically transferred from one system to another as heat, work, or a combination of both. So what in the world is a system? We'll answer that in our next video. Stay tuned.